Good morning, everyone. My name is Jade LeSchack. I'm going to be presenting work that I did last summer as part of the MathQuantum Fellowship with Nicole Younger-Halpern and Alexander LeSchack. The talk is titled Classical Non-Abelian Thermodynamics. So we're taking a departure from quantum error correction and code spaces and all that to talk a little bit about quantum dynamics. So I'm going to start with an introduction to the field of quantum thermodynamics. In the 1800s, the development of steam engines and basically the onset of the Industrial Revolution prompted scientists and engineers to try to mathematically and physically describe how energy is transformed. How do we change different forms of energy, in like mechanical energy into chemical energy, say? How does useful work dissipate as heat? Those kinds of things. With the development of quantum theory in the 1900s, we had to extend the field to be able to apply thermodynamic laws and phenomena to quantum systems. A very active area of research in quantum thermodynamics recently is the subfield of non-commutation of conserved quantities. What do I mean by that? In thermodynamics, it's very common to consider a system inside an environment E. They're exchanging quantities. We'll call the first one Q sub A and another such quantity Q sub B. These quantities are conserved globally by both the system and the environment, and they can be things like spin, particle number, or heat. Historically, researchers have implicitly assumed that these quantities commute with each other, so that Q sub A and Q sub B can be measured simultaneously. However, in this subfield, we ask, what if that is not the case? What if these two quantities do not commute? Therefore, we cannot measure them simultaneously. Non-commutation is fundamental to quantum theory, and leaving out this assumption misses out on a lot of really interesting physics. So with this now new assumption that we have, that's equivalent to saying that the system has a non-abelian symmetry. And a lot of work that has been done on non-commutation of conserved quantities can be found in this perspective published in Nature, done by the group as a whole. So it introduces a lot of the fields that non-commutation touches in quantum thermodynamics. So for some background on this specific phenomena that we'll be looking today, let's look at first at this quantum system where we take a set of qubits and we call a small subset of those qubits the system and treat the rest of them as the environment E. Total spin components of these qubits do not commute with each other for orthogonal total spin components. So total spin X and total spin Y do not commute. They obey the usual commutation relations that we're familiar with in quantum mechanics. We would like to understand how this, what analog this has in classical systems. So for a classical system, we might say that the classical analog of a qubit is a symmetric spinning top. We can again consider a subset of those spinning tops to be the system and the rest of them as the environment E. Each spinning top has an angular momentum component along the X direction, the Y direction, and the Z direction, but these are just numbers. We can measure them simultaneously. So they will commute with each other. Where then does non-commutation appear in a classical system? Well, angular momentum is the generator of rotations, and rotations in 3 dimensions do not commute. That is, if we have a rigid body and we rotate it first around the x-axis and then around the z-axis, its final position is not the same as rotating that rigid body around the z-axis first and then the x-axis. Moving further into what the thermodynamic phenomena that we're going to be looking at, we have to give some background on local versus global interactions and evolution. So in a quantum system, we would call a local, or we call gates that act on different qubits gates. They're unitaries, and a local unitary is one that just acts on a small subset of the qubits. A global unitary is one that acts on all of the qubits. Same thing in classical systems. For quantum systems, local interactions without restrictions can implement all global evolutions, and this can be seen in the universality of 2-qubit gates. So you can have any 2-qubit gates and they can implement all global interactions for any system size of your qubits. This is reiterated in a paper by Iman Marvian, whose work a lot of this is based off of, because he's classified the possibilities of local gates and global evolutions in quantum systems. Yeah, so what we did in this project is we wanted to focus on the local interactions for classical systems. So trying to understand how classical interactions between local sets of qubits, if they can realize global evolutions of the entire system. So over the last summer, I only focused on the local interactions themselves. So we considered the classical analog of a two-body interaction obeying a non-abelian symmetry. And we wanted to understand how these tops evolve. I was focused on creating numerical simulations of these dynamics. But first, I'll introduce what this local interaction looked like. So we had two symmetric spinning tops, A and B. The potential energy term is how they're interacting, and we define that as the dot product between the vector of their long axes. So the direction of their long axes, each top's long axes will be their vector position, I should say. And then the total kinetic energy is just the sum of the individual kinetic energies that we know from classical mechanics. We solve for the dynamics of each top using Euler-Lagrange equations. So the Lagrangian is just the potential energy subtracted from the total kinetic energy. And we use Euler angles as our generalized coordinates. Euler angles connect a rotating frame to a static frame when we're looking at rigid bodies' motions. And after a bunch of math that we put into Mathematica, we received back 6 differential equations that, after solving them with different initial conditions, give us the dynamics of these two tops. So we looked at two tops beginning with their long axes pointing in arbitrary directions, and we found that the tops precess about the axis that bisects the angle between them. So the orange axis is the angle that bisects the two top vectors. So you can imagine the red and the blue vector are, again, tops A and B pointing in just two arbitrary directions. Here they happen to be like pi over 4 in space or something like that, pi over 4 from each angle. And yes, they'll precess about this axis. This kind of makes sense because a dot product is defined as the magnitude of two vectors multiplied by the cosine of the angle between them, and geometrically it's also how much overlap two vectors will have in space. So yeah, we wanted to numerically see what happens. We have some analytical preliminary results that kind of support this. Yeah. So conclusion from this work is that non-commutation appears everywhere, not only in quantum systems, but also in classical systems. So we can gain more insight into quantum systems by probing non-commutation in classical systems. Hope this talk was just a brief, good introduction to what the subfield was and also the work that we did last summer. Since last summer, we haven't picked up this project again because we were working on different projects in the group. But yeah, those are the preliminary results. And I'd like to thank the people who helped me work on this project: Dr. Alexander LeSchack, Dr. Nicole Younger-Halpern, Dr. Yushin Wang, and Dr. Billy Brash had some great insights that really helped. And the rest of the Quantum Steampunk group, my MathQuantum and Trend peers from last summer, and of course, the program director, Daniel Serrano. So, thank you.